Hello, pre-calc friends. Welcome to Chapter 7. Chapter 7 is all about vectors. For a lot of you who have taken physics, you might have heard or studied about vectors already, but we just get sort of the math part of vectors done this year, and we actually don't go too far, but it's a fun chapter, and it's a nice break definitely from the difficulty of Chapter 6 that we just finished. So basically, guys, if you ever want to think of a vector, just think of an arrow. That's basically what a vector is. And notice that a vector, or an arrow, has two things. First of all, it has a certain length. That's how long that vector is. Not only that, it also has a direction. So vectors are always known by having two things here. They always have a direction, which way they're pointing, and they always have a magnitude, which is another word for our length or size. So this would be the magnitude, how long is that vector, and this would be the direction, which way it's going. Right now, it looks like the direction of this vector seems to be kind of northeast-ish or so that would be the direction of that vector. And we'll talk more about how we find those angles later. So you can see all these different types of vectors here, and they're all pointing in different directions, and some of them, maybe are about the same magnitude. These look like they're about the same length, but definitely not the same direction, because you can see the arrowheads are pointing in different ways. This one's a very long vector, so it's got a bigger magnitude, and this one's got a smaller magnitude, but they're all going in different directions as well. Over here, you can probably say that these two vectors are both the same magnitude, and you can see they actually have a measurement. This one is 700, whether it's 700 miles or feet or meters. This one's also 700, so they have the same magnitude, and they look like they actually are going in the exact same direction. So we can say those two vectors are equal because they have the same magnitude and same direction. And you notice the notation that we give here is usually a lowercase letter. Sometimes books will write it like this, so use a lowercase, and they'll use sort of a miniature vector on top. That's vector u, and that's vector v. So either way. Over here, if you look at vector w, it has the same magnitude, right? It's also 700, but is the direction the same? No, it's not. It's going basically to the west. So u and v are equal vectors, but w is not an equal vector. When we talked about magnitude, we'll give the absolute value sign. That's the absolute value of vector v, meaning that's the magnitude. What's the magnitude of u? We use this symbol here. And according to the vectors over here, the magnitude of vector v is 700. And the magnitude of vector u is also 700. So we use the absolute value symbol. It doesn't mean make it positive or anything. It just means what is the magnitude of that vector. Vectors are great in terms of where we can use them in real life. Here's a couple examples here, and you can sort of guess what's probably going on. If you look at this picture here, I would look at that and I'd see how vectors are kind of small in the middle, a little bit bigger on the outside, some different colors as well, but they all seem to be sort of coming away from these areas. This is actually a vector representation of magnets. Over here on the second one, you see some greater, longer magnitude vectors on the left, and maybe some smaller ones in the middle. I could guess that maybe this one's wind. And the last one here, beautiful colors. All I see really are arrowheads, but then when you go on the outside, you see a little bit greater magnitudes, longer vectors, and different colors. This makes you think maybe of heat, where heat has lighter colors on the inside and darker on the outside. So I don't know. All different ways of experimenting with vectors. They're great in real life. But one of the best things we can do is work with them algebraically. How can we actually manipulate them and use them in math? Well, there's a couple different ways. First of all, notice that I put vector v here on a coordinate plane. And lengthwise, I'm not exactly sure how long he is, but his magnitude is about this long here. And his direction is, sort of down and a little bit to the right. That's vector v. What we can do is we can take that and break it down into its components. How much left and right is he going, and how much up and down is he going? So if you think about it this way, if I take him and I just measure him in terms of how far left and right does he travel, from the beginning, from his endpoint to his arrowhead, how far has he traveled left and right? And then also we can take a look and see, well, how far has he traveled up and down from his tail to his head? About that distance. So what we can do is we can break those two components and write it as a component form. So it looks like to go from the tail of the vector to the head of the vector, I traveled to the right 2. So that would be a positive 2 here in my component form. That's a left and right movement, so it sort of represents an x horizontal movement here. How about up and down? Looks over here that he traveled down. He traveled 1, 2, 3, 4 boxes down. That would be a -4 down in the y direction. So vector v can be written as the component form of a horizontal component and a vertical component. And that's basically just tells you how far he traveled in which direction. This says basically he moves to the right 2 and down 4. And the good thing is I can take that measurement and put him anywhere I like on this coordinate plane. It'll mean exactly the same thing. If I give you this, that is actually the exact same vector v as we saw before. Why? Because he has the same component form. He travels 2 to the right and 4 down. So that vector is the same vector v that we started with. He has the same magnitude and the same direction. Maybe we can do the same thing with vector AB down here. Notice I called it AB because he starts at A and he ends at B. So notation-wise, I'll call him vector AB. It looks like that. And again, the tail is at A and the head is at B. Well, let's check and see. What's the overall horizontal movement from A to B, from the tail to the head? If I go all the way to here, that's to the right. So that's a positive x change. Let me count my boxes. 1, 2, 3, 4, 5, 6. That's 7 boxes to the right. So his x change would be 7. Now, how about up and down? Well, it looks like he goes a movement overall of up. So that's a positive y change. Now, if I count my boxes, it's a positive 3 boxes. So overall, I can say that his component form would be x comma y. It would be positive 7 comma positive 3. That's the component form of vector AB. So component form basically just breaks down our vectors into components. And as long as he's traveling a distance of 7 and up 3, that's the same vector. That's also vector AB. That's a great thing I love about vectors. You can just literally pick them up and move them anywhere you like. As long as you have the same magnitude and the same direction, you have the same vector. So you're good to go. Now, the way we just did it now, that was great. We looked at A and B, and we just looked at overall changes in x and changes in y, and that's fine. But you know what? An even better way. If I give you point A, if we look at that coordinate plane, A is at 1, comma, -5, and B is at 8, comma, what is B? -1. Yes, I agree, -1. Actually, I'm sorry, let me change that. I think this is actually at 1, comma, -4, Mr. Brown. I gotta count my boxes. Okay, well, my tail is here, and my head is here, because the arrow head is at A, and the tail, let me take that back. Mr. Brown got them all mixed up again. Apologies. The arrowhead is easy because it's literally the arrowhead. So here's B is the head, and A is the tail of it. Apologies. Okay, now that we got that fixed, a great way of doing this using coordinates would be what we call the head minus tail. You're going to literally take the head coordinate, which was B, take that coordinate and subtract the coordinate from A. Watch what happens. We know that we should get 7, comma 3 over here, right? That's my component form. Well, let's try it using the actual coordinates. Okay, so let me open up. And notice the notation here. I've got these little pointy brackets here, and that's for component form versus the curved parentheses, which are for coordinate points. Points have the parentheses. Vectors have the pointy brackets for component form. Okay, how about B minus A? And this is the BX minus the AX and the BY minus the AY. Here we go. Let's do the BX value was 8 minus the head, the tail value is 1. So I took the x minus the x, comma. How about head minus tail for the A? Okay. So head minus tail should be -1 minus a -4. All right. So I basically took the head point, and again, the head point was 8, comma, -1, and subtracting the tail point. Tail and tail. So head minus tail and head minus tail. Okay. And overall, these are x's and these are y's. All right. Did we get the same answer? Let's see. 8 minus 1, yes. -1 minus a minus is really +4. And we did it. There we go. So apologies for little bumps there. But head minus tail is really good when I give you the coordinate points, which we'll see actually more often. You can do HMT or head minus tail, and that'll give you the coordinate points. Let's try some. All right, well, here we go. I've got A and I've got B, and I want to look at this vector here. That means A is the tail, and B is the head of it, because it has the arrow head. So if I want to do component form, I need to do head minus tail. Let's see. Let's open up our pointy brackets. Let's do head minus tail. Here's our head, and here's our tail. So we'll do 9 minus 4, and then we'll do -1 minus 2. Simplify, and I get this vector in component form would be 5, -3. And that would be head minus tail. And if I drew that on a coordinate plane really quick, if I just estimate 4, 2 is about here, there's A, and 9, -1's over here, that's B. And if I actually drew that vector, that's starting at A and going to B, does it look like overall, did I travel +5 in the x direction and -3 in the y direction? And it does. So we know we're right. Okay, head minus tail component form. Now for number 2, remember what these absolute value means? Yep, we want to find magnitude. So I want to find the magnitude of that vector. How long is it? Well, you know what? We can actually use our component form to help us out. Because if you think about it, I want a distance of 5 and 3. So actually look what shape I made. That means this length up on top is 5, and this length down here is 3. Well, I want to find this length right here. What is the magnitude of B? And basically, let's just think about Pythagorean, if I call that C. So a great way to find this is using Pythagorean. This would be the square root of A squared plus B squared. And if I work on that, I get basically it's the square root of 34. 25 plus 9 is 34. I don't think I can simplify that radical any more than that, so that is a length of 34. And there you go. So magnitude, again, magnitude is basically like Pythagorean. I'll put that off to the side. You can write that in your notes too. Basically use Pythagorean. And the long way is just A squared plus B squared equals C squared. And for solving for C, I just think of it as this. And the good thing is, the A's and the B's are actually the same A and B that you have when you're in component form. So if you know your component form of 5, -3, you can literally just plug those values for A and B into your Pythagorean, which is what we basically just did. So there you go, folks. There's a little introduction to what vectors are and how they work. And later we'll get into how well they play with others when you do operations. Nice, fun stuff. Good job, everybody.